Okay, today we're going to study how to find the limits using the limit laws and other methods. Okay, now first, let me mention the very important fact. Okay, it says that if f is an elementary function and I is the domain of the function, okay, elementary function means the function is defined by combine all many well-known functions such like square x and sine x, cosine x, blah, blah, then it has a domain, okay? Then if you have a number inside the interval, okay, which is domain, okay? Then the limit of the function as x approaches a is just equal to the value of the function. It's very simple. It's easy to evaluate, okay? All you have to do is just evaluate the function using evaluate the function at a particular given point, okay? Now, if the number a is the left end point of the interval, but still is part of the interval, okay? So the interval could be left hand, it could be closed. Then you can only talk about right hand limit as x approaches a from positive side. Then still the limit exists and is going to be the value of the function at that number, okay? Okay, so this is a very important fact we can use. We don't need to prove it. So let's look at some example. The first example is to find the limit of x squared minus 3x plus 1 as x approaches 2. Okay, look at that. This function, the domain of this function is a whole line, okay? Because polynomial is defined for any x. So the number 2 is inside the domain, okay? So all you have to do is just evaluate the function at 2. Then you can get to it quickly. Now, the next problem. It's a square root of x minus 2 plus 3. And the limit is the right-hand limit as x approaches 2 from right-hand side. So this function, look at this function. Clearly, the domain of this function is going to be x greater than or equal to 2. So it's the interval from 2 to infinity, 2 is included. 2 is the left-hand point. It's in the interval, is in the domain, okay, but it's not interior point. Right, so you needed to, you can still use a factor to find limit. All you have to do is the right-hand limit of this function is going to be the value function of the 2. That's it. So let's check. So it's going to be 3. Let's move on to the next problem. This is a limit of x square root x squared plus 1 divided by 2x minus 3 as x approaches 2. So first let's find the domain of this function. Yeah, look at this function. When it's undefined, well, the numerator is always positive. The denominator, we don't know, but we have to make sure the denominator must be positive. Okay, 2x minus must be positive. Cannot be 0, right? But all you need is to solve this inequality. Okay, so 2x minus is greater than 0. X should be greater than 3 over 2. So you get an interval, you get domain, which is the interval, open interval, from negative 3 over, from 3 over 2 to infinity. But 3 over 2 is not included in the interval. Okay. and the function is not defined at that number. So in order to find the limit, you have to find a different ways to do it. You cannot just evaluate the function at 3/2 because the function is not defined. But does not mean the limit does not exist. Right? Oh, yeah. The limit as x approaches 3/2 does not exist. But the 2 is in the interval greater than 3/2. So you still can evaluate, to find this limit, you just need to evaluate the function at the 2. So you get square 5. But what I was saying that if I ask you to find limit as x approaches 3/2 from right hand side, the limit doesn't. You cannot evaluate find the limit by evaluate the function at 3/2. Here's another example. Yeah, just not same example. Just let me say a little bit more about this. Okay, so the same function, square of x squared plus 1 over 2x minus 3. So this time we're going to find the right-hand limit as x approaches 3/2 from right-hand side, from positive side. So this time 3/2 is not the end point of the domain, which is the interval. So in order to find the limit, you have to check how does the numerator approach. Okay, how does the denominator approach it? Okay, so x approaches 3/2 from positive side means x approaches 3/2, x greater than 3/2. That means the difference, x minus 3/2 approaches 0, x minus 3/2 positive. Well, at least first of all, the numerator, I know that x squared plus 1 approaches 3/2 squared plus 1, which is 13/4. It's a positive number. But how about the denominator, 2x minus 3? Yeah, 2x minus 3 approaches 0 from positive side. So I put user's notation 0 plus. Now, 0 plus has no meaning, but I just tell you this is a limit. Okay? So this should be equal to positive infinity. Because the denominator getting smaller and smaller, it's positive, then the fraction, okay, the quotient, okay, is getting larger and larger. Positive, large. Okay? So that's why the limit is going to be positive infinity. Okay? Now, let's move on, okay, to look at the next problem. We are going to find the limit of x squared plus x minus 6 over x minus 2 as x approaches 2. And look at this fraction. This fraction, the domain is the whole set of the whole line, but by removing the number 2. So it consists of 2 open intervals from negative infinity to 2, from 2 to positive infinity. So when you plug 2, yeah, so you cannot evaluate the function at 2 in order to find the limit. 2 is not in the interval, it's not in the domain of the function. So you have to find different ways to find the limit. You will see that there's 2 intervals, okay? So maybe we should look at the right-hand limit, the left-hand limit. Or look at the numerator. You find out the numerator, when you plug 2 for x, it's 0. That means the numerator has a factor of x minus 2. Great. That means you probably can cancel x minus 2. Then you don't need to go through the left-hand limit, the right-hand limit to determine the limit. Okay, so let's do it. The factor x squared plus x minus 6. Then the quotient can be simplified to x plus 3. Okay, now this identity holds for x not equal to 2. And then when you let x go to 2, you just need to focus on x plus 3. And clearly x plus 3 approaches 2 plus 3, which is 5, as x approaches 2. Okay? Yeah, as x approaches 2, and x squared plus x minus 6 over x minus 2, which is equal to x plus 3, right? Approaches 2 plus 3, and that is 5. Therefore, the limit is going to be 5. Okay, next problem. Let's find out x squared as a limit of x squared plus 3x divided by x squared minus x minus 12. That's x approaches 4. So first of all, let's check whether the denominator is going to be 0 when x equals 4. Okay. You solve x squared minus x minus 12 equals 0. Solve this equation. You factor it, you get x minus 4 times x plus 3. So there are two solutions. X equals 4, x equals negative 3. So the domain of this function consists of 3 intervals. You cannot say negative 3 is an end point of the interval. That's 3 intervals. Okay, and the function is not defined at negative 3 and 4. But you can talk about right-hand limit, left-hand limit at those numbers. But yeah, we're talking about the limit as x approaches 4, and 4, the function is not defined at 4, right? So we simplify the quotient. So you get x over x minus 4. That's good enough. All right. So now you have a function not defined at 4, but defined on both sides of 4. So you can, to understand the limit, you have to look at the limit, the right-hand limit, left-hand limit. So first, okay. Right, think about this. Yeah, let's look at the right-hand limit as x approaches 4. So x approaches 4 right-hand side means x minus 4 approaches 0, x minus 4 greater than 0. Therefore, the quotient approaches 4 over 0 plus. Okay, this is positive infinity. So therefore, the right-hand limit of this quotient x squared plus 3x over x squared minus x minus 4 is going to be positive infinity. Then you will look at this another case. X approaches 4 from negative side. And similarly, this is equivalent to x minus 4 approaches 0, but x minus 4 is negative. Okay, then x over x minus 4 approaches negative infinity, and which is the limit of the original function as x approaches from negative side. Right, great. So now the function approaches two different values as x approaches 4 from left-hand side, left from right-hand side. So therefore, the limit doesn't exist. You cannot say the limit equals to infinity, because you get two different, completely different infinite number. Okay, so you can only say that limit doesn't exist. Okay, so let's look at 2 plus h cubed minus 8 divided by h as x as h approaches 0. Now, to look at, when you plug 0 for h, for h in the numerator and denominator, they're both 0. So I think the numerator contains the fact of h. So h eventually can be simplified. Yeah, as a fraction eventually can be simplified, then you can quickly get limit as h approaches 0. Okay. So the interval, the domain the domain of the function is an interval. It consists of two intervals, yeah, from negative infinity to 0 and from 0 to positive infinity. Okay. So now let's look at the ratio. So the ratio, in order to get the fact of h in the numerator, we have to expand it. Okay, so be 2 cubed plus 3 to square h plus 3 to h squared plus h cubed minus 8 divided by h. So you can simplify, right? You get rid of 8, then you take the h out. Then you simplify. You get 12 plus 6 is 6h plus h squared. Now clearly, as h approaches 0, this approaches 12. The second term and third term approaches 0. Therefore, the limit of the above function as h approaches 0 is going to be 12. 12 is the limit. Right, let's move on. Yeah, let's recall some formulas. You may need it in when doing homework. So a plus b cubed is a cubed plus 3a squared, b plus 3ab squared plus b cubed. Another one is a cubed minus b cubed. Right, equals what? Do you remember? So it's a minus b times a squared plus ab plus b squared. There's also another one, a cubed plus b cubed, which is going to be a plus b, and parentheses a squared minus ab plus b squared. Right, so those are the very important formulas, and we're supposed to know them. Okay, now let's take a look at another example. Okay, find the limit of x to the fourth power minus 1 divided by x cubed minus 1 as x approaches 1. So you see that when you plug 1 for x into the numerator and denominator, both are 0. So both contain a factor of x minus 1. So let's try to factor x minus 1 from the numerator and from the denominator. Okay, can you do that? X minus 4, x to the first power minus 1 should be x minus 1 times something, right? X cubed minus 1 should be x minus 1 times something. Let's do it. So x to the first power minus 1 is going to be x to the first power. Well, wait a minute. X should be x squared and square minus 1 squared. And that is going to be x squared minus 1 times x squared plus 1. And let's continue. X squared minus 1 is going to be x minus 1 times x plus 1 and times x squared plus 1. And x cubed minus 1 will be x cubed minus 1 cubed. Here will be x minus 1 times x squared plus x plus 1. Then the quotient. The numerator and denominator both contain factor of x minus 1. So that can be cancelled out. Now, look at the new expression. It's a little bit more complicated. But when plug 1 for x, the denominator is not going to be 0. Okay, so x squared plus x plus 1 actually never be 0 for any x. Who can prove this statement? Never be 0 for any x. Yeah, it's a good exercise. But let's continue. Right, so since x squared plus x plus 1 never be 0 for any x, then as x approaches 1, all you have to do is just plug 1 for x into the numerator and the denominator. So the answer is going to be 4 over 3. Okay, therefore the limit is going to be 4 over 3. Now, it's a surprise, right? We did not expect such limit at the very beginning. All right, let's move on. Find the limit of the function 1 of x minus 1 of x squared plus x as x approaches. Now, this is quite different from the previous example. There's a difference of two functions. Don't be scared. Okay? You know, we think we can cancel some factors from numerator to denominator, right? But this is a difference, not a quotient. It's okay. We just combine them into one fraction. Can we do that? Yes, right? So you still can get similar functions like before. 1 of x minus 1 of x squared plus x is going to be 1 of x minus 1 of x times x plus 1. So it's easy to get common denominator. Just multiply the first fraction by x plus 1. then you get a common denominator. Then just look at the difference of the numerator, which is going to be x plus 1 minus 1, that's just x. So denominator is x times x plus 1. But you're surprised, you have a numerator, 1x, denominator equal to x, so therefore they cancel out. And you get very simple expression, which is 1 of x plus 1. This holds when x is not going to be 0, okay? So now as x approaches 0, you just need to focus on 1 over x plus 1. What is that limit? Simple. Just plug 0 for x. You can evaluate. Then you get the limit. Right. So the limit is going to be 1. All right. So let's move on. Okay, let's find the limit as x approaches 2. And this is square x minus square root of 2 divided by x minus 2. All right, so we're going to look at the limit of x square x minus square root 2 divided by x minus 2 as x approaches 2. Now, you plug 2 for x into the denominator and numerator. You find them both as 0. So you think about it, the numerator should have a factor of x minus 2. But how can you find it? There's a standard way to do it. If you see x squared x minus 2, then you multiply it by x squared x plus square root 2. Okay, then the numerator actually has become x minus 2. All right, so now you get x minus 2 on the numerator, right? Then you cancel x minus 2, then you get 1 over square x plus square root 2. Right, so this is good. Okay. Yeah, in order to get the factor of x minus 2 from the numerator, you have to multiply the numerator by square root x plus square root 2. So look at this function. The interval of this function is the set of x. X is not going to be 2, and x cannot be negative. Okay, so the interval actually the domain consists of 2 intervals, from 0 to 2 and from 2 to infinity. Right. So you cannot directly plug 2 for x into the function evaluate. You have to look at the simplified one. And when x approaches 2, the simplified expression clearly approaches 1 over square root 2 plus square root 2, which is 1 over 2 times square root 2. Okay, so now then we get the limit, okay, which is 1 over 2 times square root 2. All right, so the formula we're using here is the following. So when you see square root x minus square root b, if you want to get rid of radical, you just multiply by square root a plus square root b. Then you get square root a square minus square root b square, and then just a minus b. Okay, and both a, b cannot be negative greater than 0. All right, let's move on. This is a standard technique, okay? Don't worry. Yeah, but you have to know that, right? When you see radicals, how do you do that? So now the next one is a similar type, but it's not radical. You have to simplify the expression, get rid of h. So 1 over x plus h minus 1 over x divided by h. That requires very basic algebra skill. Okay. So you simplify the numerator, you have to combine 2 terms in the numerator. then eventually you get a factor of h, and you get rid of h by this division. Okay, so let's look at the numerator. 1 over x plus h minus 1 over x divided by h. If we combine the two terms in the numerator, you get h is negative h divided by x times x plus h. Did you see that? Yeah. So the numerator here of the fraction in the numerator will be negative h divided by x times x plus h. So you simplify this notation, it's going to be negative h over x times x plus h divided by h. So h cancel out, you get negative 1 over x times x plus h. Okay, so now the simplified version is really simple. It's going to be negative 1 over x times x plus h. So when h approaches 0, you get negative 1 over x squared. Now clearly at the very beginning we should know that x is not going to be 0. Otherwise 1 over x is already not defined. Okay, so you get a limit negative 1 over x squared. Right. Let's complete the solution. Right. I'm going to talk about a very important theorem. It's called I think it's called squeeze theorem. Yeah, it's the squeeze theorem. Squeeze theorem. Roughly speaking, if the function f of x is between two functions and both sides approach the same number, L, then the one in the middle must approach that number. That's like, it's clear, right? Just like, you have two friends on each side that go with you together toward the same place. Okay? And you must go to that place too. Okay? Clear, right? Okay. So the limit of maybe it's easy to find limits for the g of x, for the h of x, as x approaches a. If they have the same limit, then the one in the middle maybe a little bit more complicated, still have the same limit, L. Now the special case is the absolute value x is less than or equal to g of x. So here only have two functions. Okay, if g of x approaches 0 as x approaches a, then f of x approaches 0 too, as x approaches a. Now, why this is true? Well, it's clear, right? Because absolute x is bounded by g of x. G of x approaches 0. Then it forces absolute x approaches 0. And then f of x must approach 0. You can also look at this. F of x is less than or equal to g of x, greater than or equal to negative g of x. Then by the squeeze theorem, both sides approach 0. Then the one in the middle must approach 0. If both sides approach 0, okay, then the one in the middle must approach 0. Okay. This is a pretty useful theorem in order to prove something approaches 0. Okay, look at the following limit. this function is defined to be x times sine 1 of x. As x approaches 0, sine 1 of x, sine 1 of x does not have a limit. Why? Because 1 of x, it's always up and down, up. It's getting larger, larger. Now, if you always assume x approaches from positive side, then 1 of x approaches infinity, positive infinity. But sine of the 1 of x change the values. It does not approach a number, same number. Okay. However, the absolute value of sine theta is always equal, less than equal to 1. So if you look at the term x, the factor x in front of sine 1 of x, and that x plays a very key role here. So actually, that x forces the product approaches 0. Let's see it. Absolute of x times sine 1 of x is less than equal to absolute value of x. So if absolute value of x approaches 0, yeah, which is an assumption, yes, then it forces x times sine 1 of x approaches 0. Okay, that. Now we're talking about sine. So now we're talking about the limit involves trigonometric functions. Okay. So let's take a look at another important limit. The limit of sine 1 of x, sine x over x as x approaches 0. Yeah, let's look at that limit. Yeah, find the limit of sine x over x as x approaches 0. Yeah, not this one. Yeah, let's erase it. Yeah, look at this. Look at this function. And you see that when you plug 0 for x into numerator, denominator, both 0. So it's like a 0 over 0. But denominator definitely it's clear has a factor of x. But the numerator, you cannot factor it. Sine x is not sine times x. So let's assume x greater than 0. And actually we can, using the picture, to interpret the meaning of sine x and x. Okay. So draw the circle with unit with radius equal 1. And you draw two triangles. The vertical side of the right triangle, the two vertical sides. The length of the first one on the left is just sine x. The arc length is x, okay, corresponding to the angle denoted by x. Then the vertical side on the right-hand side is tangent x. X is the angle. X can be viewed as an angle. Also can be viewed as the length of the arc length of that piece on the unit circle. So clearly, the arc length x is between sine x and the tangent x. This is a trivial inequality, but it's not easy to see that at the very beginning, right? So tangent x is sine x over cosine x. So if you rewrite the above inequality, you get sine x over x greater than less than 1, greater than cosine x. Now, this is a good example where you can use the squeeze theorem. We don't know the exact value of sine x of x as x approaches 0, but it's always between cosine x and 1. So look at the cosine x. Cosine x approaches 1 as x approaches 0. So that forces sine x of x approaches 0, approaches 1 as x approaches 0. Right, now for x less than 0, you can express x as negative absolute of x. So sine x of x can be written as sine negative absolute x over negative absolute x. So you can take a negative sign out and the negative sign cancelled out. So you can change sine x of x to sine absolute x over absolute x. So absolute x is positive. So we already proved that this one approaches 1 as x approaches 0, or as absolute x approaches 0. So we get the following result. Limit of sine x over x as x approaches 0 from left-hand side is 1. And we know from right-hand side also it's going to be 1. So therefore, the limit of sine x over x as x approaches 0 is always equal 1. Okay. So let's look at the next problem, which is going to be the application of above example. Find the limit of 1 minus cosine x over x squared as x approaches 0. I don't have a picture for this, but how do I solve the problem using the above example? Well, we have to recall some formulas in trigonometric geometry. I'm going to simplify the numerator, change it to subtraction to single trigonometric function. All right, so let's see. Cosine 2 theta equals cosine square theta minus sine square theta. And that, yeah, cosine 2 theta is going to be cosine square theta minus sine square theta equals 1 minus 2 sine square theta equals 2 cosine square theta minus 1. You can solve for sine square theta, which is 1 minus cosine 2 theta divided by 2. You can also solve for cosine square theta. That is going to be cosine 1 plus cosine 2 theta divided by 2. All right. Now we're going to apply these formulas to the above problem. I have to change 1 minus cosine x. Okay. 1 minus cosine x is going to be twice of sine square half of x. All right, so 1 minus cosine x divided by x squared is going to be 2 sine square half of x divided by x squared. And then we're almost done. Okay, we have to put in the bigger parenthesis, take 2 out. Be sine half of x divided by x, then square. Then you have to make the denominator also half of x, right? So what do? You divide x by 2 and multiply by 2. That's a pretty standard technique. Multiply by 2. Okay. Then square. Now let's circle the quotient, the special quotient. So sine half of x divided by half of x. Clearly it approaches 1 as x approaches 0. So the final result is 2 times 1 over 2 squared, which is simplified to 1/2. Okay, so the result is 1/2. Now let's look at some piecewise defined function. So the function is defined as x squared plus 1 if x less than 1, x squared minus 2 squared plus k if x greater than or equal to 1. So this function, the domain of this function is a whole line. It's defined everywhere. What is the question? The question is, determine the value of k such that the right hand limit equals left hand limit of the function. And that means the limit of the function exists. Exists is equivalent to saying that the right hand limit equals left hand limit. All right, so let's find the right hand limit. Now, as x approaches from right hand side, then you have to use one of the pieces for that function, because x is greater than 1, right? X greater than 1, then the function equals x minus 2 squared plus k. And as x approaches 1, and clearly it's needed to plug 1 for x into the expression. Then you find the limit, which is 1 plus k. Then you also look at the left-hand limit. That, and you can easily get the limit is 2. So they must be equal, right? Okay, so k is equal to what? So if k equals what? The limit of this function is going to be 2. Notice that the value of the function is at the range 2. It's defined. Actually, is given by the, in this case, right? It's going to be 2 because k equals 1. Right. So let's look at another piecewise defined function. But this time, yeah, the function is defined by 2 pieces, but it's not like on right-hand side or left-hand side of 0. Actually, when x is not going to be 0, you get sine 2x over 3x. When x equals 0, just some constant. But we have to find a case such that the limit of the function as x approaches 0 is going to be the value of the function. What is the value function? The value function is k. All you have to do is to find the limit as x approaches 0. Okay, then you can determine the value of k. But this is sine 2x over 3x. How can I find the limit as x approaches 0? But remember, sine x over x approaches 1 as x approaches 0. But now here I have sine 2x over 3x. So how can I do that? How can I find the limit? You have to, it's for x not equal to 0, it's going to sine 3x over 2x. Sine 2x over 3x, sorry. And maybe it's better to introduce a new variable. Okay, well, let's see that to be sine 2x. So the numerator is just sine theta. The denominator is going to be 3 over 2 times theta. Okay, how do I do that? Just replace x by half of theta. Okay, now the constant in the denominator becomes 2 over 3. But clearly sine theta over theta approaches 1, because when x approaches 0, theta approaches 0. That's why sine theta over theta approaches 1. So the limit is going to be 2 over 3. Okay, so the value of k must be equal to 2/3. Okay. Got it? I think that's enough for today's class. Make sure you finish the homework before the next lesson or before this Saturday, Sunday. I'm going to give a quiz on Monday. Okay. I apologize the first time I record the voice.